So welcome to our analysis of variance class. I'm going to be presenting with Takanobu Suzuki. My name is Taylor Randolph. We're going to take the first part, which is an exploration of the theoretical underpinnings of ANOVA and looking at assumptions and a few different things. And Takanobu is actually going to be performing this on SPSS. So here's a kind of an outline of what I'll talk about. And you can see that we're going to cover a variety of topics. First of all, I'd like people to think about this distribution. And what does this bring to mind in each of your experiences with statistics to date? Hopefully each one of you had the idea of a normal distribution or standardized distribution pop into your head, the bell curve. So what we're doing here with the t distribution is looking at this bell curve as it pertains to samples, not necessarily populations. We are going to be dealing with this same sort of prospect in a different kind of way when we're talking about ANOVA. So first of all, let's do some quick refresher on statistics. So what is the difference between the standard deviation and the variance? Hopefully, as you thought about this, you would recognize that the variance is simply the standard deviation squared, and the standard deviation is the square root of the variance. They're basically the same number, just have that bit of transformation that we do. So keep that in mind about standard deviation and variance. What do the z and t scores represent? So if you bring back that image of the normal distribution, what do the z scores and t scores represent on that normal distribution? If you said the distance between standard deviations from the mean, you are correct. You are absolutely correct. And so is it dealing with the variance or standard deviation? It's dealing with the standard deviation, right? And so I would like to ask you, are these positive or negative scores? And also think about why. So if you came up with the answer of these are both positive and negative scores, you'd be correct. And why would that be? Well, we're trying to measure the distance from the mean. So you could be above the mean, you also could be below the mean. You could standard deviations above or standard deviations below. And then this gives you a representation of a normal bell curve. And you can see the z-scores being +1, +2, +3, and also -1, -2, -3. And they allow you to do what? They allow you to locate a score within a distribution. They allow you to locate a single score and give a probability of where that score might lie in that standard distribution. So I'd like us also to consider this. What if we only use the variance to determine variations of scores? So think about that, the variance. We're only using the variance. What would the distribution look like? And would we have negative scores? What do we know about the variance? Well, the variance is always squared. So if you square something, you multiply it by itself. And so if you multiply something by itself, if it were a negative number, it becomes a positive number. If it were a positive number, it stays a positive number. When you square something, you always get a positive number. And so the distribution looks a little different. You don't have any negative scores. You have all scores that are, because you compute a score on this F distribution, you will compute an F score. And it will resemble your T and your Z, although F is always going to be dealing with a positive number. And you can see that if we get in the tail of this positively skewed distribution here, the F distribution is positively skewed, you'll find that you have less of a chance of finding a score in these tails out here. And so you see how they vary according to number and mean. So you can see that it's positively skewed. No negative numbers on that F score. And so when we're dealing with ANOVA, we're talking about increasing K, which means increasing the number of factors or groups. In fact, you run ANOVA with 2 or more. Normally, we're used to running t-tests, or excuse me, t-tests when you have only 2 groups. But on hypothesis testing, we're often interested in more than 2 groups. And t-tests are quite limited in that you'd have to, if you had 3 or more groups, you'd have to do t-tests between each one of those groups and each variant of each one of those groups. So you're looking at, if you have 3 groups, you're looking at 1 t-test, 2 t-tests, 3 t-tests to examine differences. That becomes very impractical when you get really high numbers. In analysis of variance, it's also called the F-test, is a statistical procedure that's going to test hypotheses for 1 or more factors regarding the variance among 2 or more group means, where the variance in 1 or more populations is unknown. All right, so the type of ANOVA that you use depends on the number of factors being tested. If you're doing a one-way ANOVA, you're only testing 1 factor. If you're doing a 2-way ANOVA, you're doing 2 factors, and so on. What is a factor? Well, you observe participants across each level of a factor. So you can have a within subjects design. We're not going to talk about this here, but there is a within subjects design. But you can also have between subjects design, where you're looking at independent participants, and participants are observed at each level of a factor. They have independent samples. So a one-way between subjects ANOVA is the most basic type. And in this type of ANOVA, different participants are observed at each level of 1 factor. The notation is a little bit different than what we have dealt with so far, in that we're starting to use different symbols. F obviously stands for the test, but there are also some things that we need to take into consideration, like K. So your lowercase n equals the number of participants in your groups. Your uppercase n is your total number of participants in your study. And your lowercase k, it indicates the number of your groups or factors. So again, let's keep in mind those changes in notation. Now, there are several assumptions that we need to meet before we jump into and do ANOVA. We need to make sure that we had some random sampling. Most procedures are built on that presumption. You also want the scores to have independence of variables. So that means they're unrelated and not influenced by one another. You also really want this assumption of normality. Your residuals or data sets, your individual group scores and your dependent variable, each resemble, in each level of the IV, resemble a normal distribution of scores, that bell curve. And also, to get this, you need to be considerate that your scores are measured in interval ratio data. Now you have some tests that you can conduct to look for this normality. You have the Shapiro-Wilk or the Kolmogorov-Smirnov. You can also take a look at some exploratory statistics, which I think which I think Takanobu will do. You can look at skewness, kurtosis. Also, produce a histogram to look and see how the scores are distributed. You'll also want to look at if you do have some significant deviations from normality, you might consider a Kruskal-Wallis test. It's basically doing the same thing as ANOVA, except it's a non-parametric equivalent. You'll do some different things with your post-hoc tests. It won't really exactly run any, but Kruskal-Wallis is available too if you violate that assumption. We also have the homogeneity of variances assumption, which means that you have equal variances or homoscedasticity, which means that you have equal scatter. You have some graphs that we can do for that, but also Levene's test is a good measurement of that, and you want your Levene's test to be non-significant, a p-value of greater than 0.05. Now, if this assumption is violated, please know you can run the Welsh test or Brown's Forsyth test. One of the main things to consider here as you explore your data is that you account for outliers. You want to explore, it's not necessarily a hard rule assumption that you won't have any outliers, but you do want to account for them and control for them if you can. So, degrees of freedom. The degrees of freedom for one way between the subjects ANOVA is n-1. However, we report the degrees of freedom for between and within groups. These are computed as follows. You can see the first one, and we'll put these in parentheses, is k-1, the number of groups -1, and then your second degrees of freedom that you'll report with your F-score is n-k. Your overall number of participants minus the number of total groups that you have. And so you should be aware that as k, n, or n increase, so do your degrees of freedom. Your critical value gets smaller and your power increases. So you don't need as big a differences on your test to find significance. So if you do find significance, it's not just a t-test and you run and you get a statistic and you're able to determine, hey, that this variable is greater than this one. You have to do post hoc comparisons because you're dealing with 3 or more groups. The F-score that you compute will just tell you whether or not there's a difference between some of those groups. It doesn't tell you where. And your post hoc comparisons actually tell you where. So there are several to use, and I borrowed a sheet here that I like to consult. It's from another textbook for Privatera in 2016. But you can see that the Chef-A test and Bonferroni procedure are very conservative. They don't give you a whole lot of power. In fact, they're being criticized being too conservative. Tukey's HSD is commonly used in psychological research. We also have the SNK test, and the LSD test is good when you have 3 groups. If you have like 3 groups, use that LSD test because it's a pretty good indicator. It gives you the most power. So just be aware of those post hoc tests. ANOVA helps, again, we're comparing means and looking for differences. So you'll also want to look for effect size. If you do find significance, you want to look for effect size. And so there's a couple of different measures. You can look at eta squared measured or an omega squared measure. And so you'll want to report those as well when you go ahead and report your results. So the test statistic is your F-score, or your degrees of, and then it'll be followed by, in parentheses, your degrees of freedom and your p-value. Then you also want to report effect sizes for the significant results. So there's an example. Your F is, in parentheses, 2 and 27 degrees of freedom equals 3.52. The probability of making a type 1 error was less than 5%, 0.05. Eta squared value was 0.14. Which means about 14% of the difference can be accounted for here by this effect. But one may also summarize the mean, standard error, or standard deviation in a table, a figure or table in the main text. So the standard deviation and means are also important to report so people can get an idea of what exactly they are. And so you also want to summarize your post hoc test. In this case, there was a Tukey HSD, and the probability was less than 0.05, that there was significance between, you'll identify the variables as well. So there are my references. Hope this has been entertaining and also educational for you. You're welcome to come back and consult, and please contact me if you have any questions. Please be aware that Takanobu is now going to demonstrate how to run ANOVA using SPSS.